Hello Huskies, we are going to talk about explicit formulas for sequences today. And explicit does not mean bad, it means very clear and detailed. And there's a picture of an airplane on the front here, and we're going to talk about why there's an airplane there, and hopefully it'll help you remember why we need explicit formulas. Okay, so our objective for the day, I can write an explicit formula for an arithmetic or a geometric sequence. Okay. An arithmetic sequence, just to review, it adds the common difference each time. An arithmetic sequence adds or subtracts, which is adding a negative. So, for example, we have two arithmetic sequences here. The first one going from -50 to -40, -30, -20, we're adding 10 every time. And then the second one, we went from 21 to 14, 7, 0. Well, we are adding a -7 or subtracting 7. Now, just to review, a geometric sequence is a sequence where we're multiplying by a constant ratio each time. We have the number, we're multiplying by the same number every time. So, in this first sequence, 1, 5, 25, 125, we're multiplying by 5 every time. That's the constant ratio. And then on the second one, going from -16 to 8, I multiplied by, I know a lot of you are thinking, oh, I divided by 2. Well, we can't divide. You can subtract, but you can't divide. And in a geometric sequence, we're going to only talk about multiplication. And there's a reason that we're going to do it that way. It will help you write the formulas much easier later if you only think about this in terms of multiplication. So instead of dividing by 2, let's talk about this sequence as being multiplied by 1/2. But wait, we went from -16 to +8. We must have multiplied by -1/2. So what is +8 multiplied by -1/2? Oh, -4, so that works. -4 multiplied by -1/2 is +2. So our ratio here, our constant ratio, was -1/2. That was the pattern, the thing we were multiplying by every time. Okay, just a little word. There are more than these two kinds of sequences. There are other kinds of sequences. We are only going to study arithmetic and geometric. But there are sequences that are not arithmetic or geometric. They're neither. Okay, let's review recursive formulas. We talked about a recursive formula has two parts, a starting point and a pattern. And so you always need to tell me the starting point. You can start wherever you want. You can start in the beginning with the 0 term and give me whatever the starting point is, or you could start with the first term. You know, you could start with the 45th term. I don't care where you start. If you know it, you can start there. Okay, and then we have to have a pattern, and so what these symbols all mean, and we're going to talk about function notation later in the year, but for now, this f of x is saying to find the current term or the next term. You're going to take the previous term, that's this one, and do something to it. That was the pattern. So let's just review by writing a recursive formula for this sequence right here. Starts at 3, goes 5, 7, 9, 11. Okay, well, it starts at, let's just use the first term, which was 3. And what am I doing every time? I am adding 2. That's my pattern. So my recursive formula would look like f of 1 equals 3, and to find f of x, to find the next term, I will take f of x minus 1, that's a subtract, and add 2. I just have to put in those 3 missing parts. We put in which term I'm starting with, what it is, and what the pattern is. And that's how you write a recursive formula. Okay. Let's go into your classwork. We have this table here, and we're going to fill it in. So the 6th term shouldn't be too difficult because you can see that the pattern of this sequence, every time I go up like this, I am adding 2. It adds 2 every time. And so this is obviously going to be a 13 right here, but wait. How do I know what the 150th term is? That's way far away. I would have to get probably a calculator. I could do it in my head, but yuck. And then I would have to just sit there and go, okay, the 7th term is 15, the 8th term is 17, the 9th term is 19, the 10th term is 21, and just keep adding 2 over and over and over again until I get to the 150th term and figure out what that is. Well, I don't really want to do that. That's going to take a long time. So today we're talking about a different kind of equation that will allow us to jump right to any term we want. So let's go back to this, the classwork. What's the first term? The first term, this is the term number, and the value of the first term is 3. My first term was 3. So to find the 150th term, maybe you want to team up with a partner and do this recursively and just keep adding to, and keep working on it. If you're doing this at home alone, you missed out that opportunity in class to discover that the 150th term is 301. I'm just going to tell you what it is. I don't want to spend time showing you how to get there recursively. So if we want to find a better way, some of you, by struggling through that process, trying to figure out what the 150th term is, might have come up with a pattern. And that's exactly what I want you to do. I want you to see the pattern. So if you didn't see the pattern, that's okay. We're going to step through it a little at a time to help you figure out what this pattern is. So we have this table, and you can read in your classwork that we are trying to get a pattern so that we could find any term, not even the 150th term. What if I'd asked you for the 2000th term? You want to add 2000 times on there? No, not me. Okay, so let's find a better way to do this. So we already figured out in the earlier table that the 6th term was 13, and we would know then that the 7th term is 15, and we do already know that this term is 301. Like, we could fill that out. Let's just wait for a minute on what that x term means. But look at this pattern here in the middle. We started with just a 3. That was our first term. How did we get from 3 to 5? Well, we added 2. So I wrote that out as 3 plus 2. How did I get the 7? Well, I added another 2 on, but instead of writing that as 5 plus 7, I wrote it as 3 plus 2. Adding 2. So hopefully ignore what I say, and this makes sense. So how do I get from 7 to 9? Well, 3 plus 2 is 7, and so I'm going to add another 2 on there to get my 9. How did I get to 11? I would add another 2, because, that's the pattern, adding 2 every time. So you can see how this is growing. We're just adding a 2 every time and writing it out. Man, this is kind of boring. I really wish there was a shortcut for adding the same thing over and over and over again. Wait! There is. It's called multiplication. So on the right-hand side, this is using a more efficient pattern. Instead of writing out plus 2 plus 2 plus 2 over and over again, I said, well, adding 2 over and over again is the same as multiplying. So how many times did I have, how many 2's did I have in this, the 5th term? Whoops, that's not pointing where I wanted to. Right here, how many 2's did I have? 1, 2, 3, 4. So I must have 3 plus 2 4 times. And then on the next one, you can see that there's a 3 in every one of these, right? Because we started with a 3, our first term, but then I added 2 on. How many times did I add on 2 for the next row? I added 5 2's on. And then I had the 3, and I added on 6 2's. Let's go backwards and see if we can fill out some of these in the earlier. We had 3 plus 2, 2 2's. There were only 2 2's there. And then we had 3 plus only 1 2. Well, then what goes in the top one? We had a 3, but how many 2's did we add? 0. Doesn't that fit nicely into our pattern? 0, 1, 2, 3, 4, 5, 6? It does. Okay. So, still not sure. How's that going to help us get to 301? Well, I'm guessing it's going to be 3 plus 2 times something, right? Because that was the same in all the others. Well, how do I know what goes in those parentheses? Did you see any kind of relationship between what's here, what's on this side, and what is here? Let's see. Not there. There. The term number. So if we were adding 6 2's, that was for term 7. We were adding 5 2's, that was for term 6. 4 2's was for term 5. 3 2's was for term 4. So hopefully you can see that the pattern there is that it's whatever term we're looking for minus 1. That's how many times we added 2 on. Now think about why that makes sense. Remember way back at the beginning, did we add anything on our very first term? No, it was just 3 plus no 2's. So we didn't add it on every time. We only added it on the next one. And so it's like we have to subtract 1 off because it's like only after that did we start adding on the 2's. Okay. Oh, sorry. You know what would have made more sense to you here is if instead of the x I said it was 150 minus 1. Because we didn't add on to 150 times, we only added it on 149 times. So then for x, that's where we could say, well, no matter what the term is that I'm looking for, if I subtract 1 from that, and that'd be how many 2's I'm adding on, and then I add that to the 3 that was originally there, and that's how I figure out what it is. Okay, so this thing that we just discovered, this pattern, is the explicit formula for an arithmetic sequence. It's explicit because it gives you very clear and detailed directions on how to get exactly there. So copy this down. This is how you're going to write every explicit formula for an arithmetic sequence. And I'm using f of x, which is the function notation again. The first thing you're going to write is the first term. The first term. For today, we're always going to use the first term. Later, it will change and we can use whatever term we want. But for today, we're going to use the first term. And then we're going to add the pattern times x minus 1. So when we did recursive, remember, let's flash back here. What we had to come up with were just these blanks. Where are we going to start? What's the starting point? And what's the pattern? Those 3 things. Well, it should kind of sound the same. Hey, we are going to have a first term and a pattern. And then this x minus 1 is to say, well, we didn't add the pattern on the very first one, only after that, the next one we started adding the pattern on. So copy this down. This is your general explicit formula for an arithmetic sequence. Now let's use it. An explicit formula is a tool, and in class we talk about how if you wanted to take the train, say you wanted to go to Denver. You wanted to go to Denver and you took a train to get to Denver. That is going to be like a 3-day trip because that train has to go through every single little town on the way to Denver. There's no train that just starts in Salt Lake City and ends at Denver and doesn't stop anywhere in between. It has to go through all the little towns, so it takes a really long time. But if you wanted to get to Denver on an airplane, you wouldn't have to go through every little town. You get on in Salt Lake City and you get off in Denver. Well, the explicit formula is like flying on a plane. You get to skip right to whatever term you want. You don't have to go through all the little towns. Recursive is like taking the train because if you want to know what the 10th term is, you first have to know what the 9th term is. And if you want to know the 9th term, you have to know the 8th term. If you want to figure out the 8th, you'd have to know the 7th, etc., all the way back to where you started. But explicit lets you just jump right to any term you want. You don't have to know what the term was before it. So we're going to write an explicit formula now on this example, and we're going to use it. So the explicit formula we came up with up in our table looked like this: 3 plus 2 times x minus 1. Remember what this stuff means. 3 was our first term, 2 was our pattern, and x is the term we're trying to find, and we're subtracting 1 because we don't add that pattern on every single time, not the very first time, only after that do we start adding it on. And f of x is just the name of this function. You don't have to worry about that. We'll learn more about function notation later, and hopefully that'll clear up for you. One word of caution: do not add these two together. No. You can't do that because this 2 is being multiplied by the parentheses and you have to distribute it or simplify it first that way. Don't ever add that 3 to the 2 because we multiply before we add. Okay, so I know, you don't care. You just want to do your classwork. Let's use this tool to find the 218th term. This is how I'm going to write that. To find the 218th term, that would be f of 218. It's going to equal 3 plus 2 times 218 minus 1. I'm just going to evaluate this function when x is 218. I know you know how to do that. We have been doing that all year so far. Evaluate a function, add a value. So then we don't have to do anything right here. That's just telling us again what we're finding. It's like the name of the answer. And this is going to be 3 plus 2 times 217. And it ends up being 437. If you don't get 437 when you type that in your calculator, you've done order of operations wrong. Make sure you get 437. That's just the answer. The 218th term is 437. Isn't that better than adding 218 times? Yep, it is. Okay, so let's do another example. First of all, here's your sequence, -11, -3, 5, 13, and 21. Let's write an explicit formula. Well, we still need two things to write an explicit formula. We need a first term, and we need a pattern. Yikes, the handwriting, that's a T. The first term is -11, and our pattern, hopefully you can see that we are adding 8 every time. Okay, that's all we need. Now, look back on your paper to where it says the general explicit formula for an arithmetic sequence and put in the puzzle pieces where they go. So the explicit formula for this is going to be our first term plus the pattern times x minus 1. Boom, done. Now that's a good formula, that is. But there's a better formula, and maybe even a best one. You could leave it like this, and I will give you all the points. It's totally fine. It's great. But what would happen if you did distribute? What? Let's see. You would get -11 plus 8x minus 8. Okay, it's better. I got rid of the parentheses. It's a little more simple. But the best equation here would be if I simplify these like terms. And so then I'm going to have -11 plus -8 is -19. So this is actually 8x minus 19. F of x equals 8x minus 19. Wait a minute. Wait a minute. Does this remind you of something? Y equals mx plus b? What? An arithmetic sequence is actually another way of thinking about linear equations. Y equals mx plus b. I know you spent half of 8th grade doing y equals mx plus b. Boom! Arithmetic sequences. They are linear. What? That's awesome. Okay, but little side note, what we actually want to do right now is use that tool. It says on part B, use your formula to find the 739th term. We just made a tool. Here's one tool. That's a good tool. This was a better tool. This is the best tool. I don't care which one you use. They're all the same in my eyes, good, better, or best. If you only understand good right now, that's great. Hopefully we can all work up to using the best one, to being able to simplify that. So we're going to use this tool now to find the 739th term. So we want to find f of 739. The 739th term is going to equal, let's use the good one first, -11 plus 8 times 739 minus 1. Tippity type, type, type on your calculator, and you're going to get some kind of an answer. I don't have it. I don't know what it is. Okay, -11 plus 8 times 738. 5,893. 5,893. Guess what? If you use the best formula down here, and you did f of 739 equals 8 times 739 minus 19, you know what you would get? Same thing, 5,893. So you can use that tool to come up with any term in a sequence that you want. Any one. You can jump right to it, just like flying in an airplane. Okay, so let's just point out a couple of similarities and differences for you to notice, because you are going to have to memorize these formulas. And this is going to be the foundation for like half of what we do this year. It's crucial that you understand this before we go on. So the explicit formula for the recursive, how is explicit like recursive for arithmetic sequences? Well, they both need a first term and a pattern. Remember, there's a place to put each of those. And so you have to find each of those things, the first term and the pattern. How is it different? Well, an explicit formula is only one equation. Remember that a recursive formula always needs two, a starting place and a pattern. Those are two separate equations, but they're the starting point and the pattern are both inside one equation for an explicit formula. Remember that a recursive formula is like taking the train. You have to go through all the cities on the way, all the little towns. But an explicit formula is like flying in an airplane. You can jump to whatever term you want, way far away or even just close. Okay, now in the back we're going to talk about explicit formulas for geometric sequences. And the sad thing is they are different than arithmetic sequences. I know when we did recursive, all you had to do was change the plus to a times, but these are going to be different. So let's see if we can figure out what it'll look like. Here's our first sequence. Starts at 3, first term is 3. What's my pattern? 3 to 6 to 12 to 24. It looks like I am multiplying by 2. Okay, I have a first term and a pattern. I'm ready to go. I could find the 24th term. That's not very far away, but since it's geometric, it's going to be a very big number. So you could start by finding the 7th term, multiply by 2, 8th term, 9th term. See if you can figure out some kind of pattern, if you can see a better way to get there. If not, just do it recursively. Keep multiplying by 2. And you're going to end up with your 24th term as 25,165,824. That's big. Geometric sequences get very big very quickly. So now let's look in our pattern in our table, kind of like what we did on the first page. We started with a 3. Then we multiplied by 2. To get a 6, we multiplied by 2. Then we multiplied by 2 again. Then we multiplied by 2 again. So we would have 3 2s in a row. And then we did 4 2s being multiplied together. We started with a 3, multiplied 5 2s. The 7th term was 192. And so that would have been 3 times 2 times 2 times 2 times 2 times 2. Gosh, my hand is starting to get tired. I wish there was a more efficient way of writing multiplying by the same number over and over and over again. Of course there is, and it's called using exponents. So right here I multiplied a 2 on there 3 times, so that's why I have a 3 as my exponent. So what's it going to be on the next one? I had starting term, my first term was 3, and then I multiplied by 4 2s. Then I had a 3 and I multiplied by 2 5 times. I had a 3 and I multiplied by 2 6 times. Well, let's work backwards. This would have been 3 times 2 to the 2, 3 times 2 to the 1, because there was just 1 2 being multiplied. So what's here then? 3 times 2 to the 0 power. What? I hope you remember from way back in 8th grade that anything to the 0 power equals 1. And so what does 3 times 1 equal? 3. Oh, sure, that's what our first term was. It works. Okay, so then what relationship is there between this exponent and the term that we are looking for? Well, look at this one. That was a 5, but it was the 6th term. This is a 4, but it was the 5th term. So hopefully you can see that this would be 3 times 2 to the 23rd term because it was one less every time. And so a general equation would have been 3 times 2 to the x minus 1 power. That, my friends, my fellow Huskies, is your general explicit formula for a geometric sequence. This is what it looks like. Start with f of x, of course. You write your first term. And again, later we'll be able to put something different there, but for today we're just going to use the first term. And then we're going to multiply it by whatever the pattern is. And it has an exponent because exponents are the shortcuts for multiplying by the same thing over and over again. And your exponent has x minus 1 in it because we didn't multiply by 2 every time after the first time. That's when we started multiplying by 2. So we subtract off 1 to show that, oh, that very first time, right, in this table, there was no multiplying by 2 in this row. We only started on this row. Okay, so let's write an explicit, we're going to practice. Write an explicit formula for this sequence. Okay, here's our first term, 7. What's our pattern? Looks like 7 times 2 is 14. 14 times 2 is 28. Okay, we must be multiplying by 2. So if I use this formula that I just wrote, I'm going to start with f of x equals the first term times the pattern to the x minus 1 power. And that's it. I'm done. First term goes in the first, and the pattern goes in the parentheses right there. That's what we call the base. That's the thing that you were multiplying by over and over and over again. Now that we have that tool, we're going to use that tool to find the 35th term. Remember, explicit formulas let you jump. You can fly right to the 35th term. You don't have to take a train that lasts days long to get there. You're going to plug in a 35 for x because we're trying to find the 35th term. And we got to subtract 1 because we didn't multiply by 2 every time, only after the first one. When you type this in your calculator, please, 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 please be so careful. If you're using a crapulator at home, I don't know what kind of order of operations it does, but most calculators don't know that you want these two, the 35 and the subtracting 1 grouped together. You have to keep those in parentheses because if not, if you just type 7 times 2 to the 35 minus 1 power, your calculator is going to find 2 to the 35th power and then subtract 1. It can't read your mind. It doesn't know that that's not what you mean. So, you know, first of all, just use your brain. 35 minus 1 is 34. If you want to type in 7 times 2 to the 34th power, there you go, you won't have any problems. But if you feel like you don't want to subtract 1 in your head, then you had better put that in parentheses right there and type it in exactly like that. Otherwise, you're going to get the wrong answer. Okay, let's say you typed it incorrectly, and here's the way you're going to know you typed it incorrectly, because if you typed it incorrectly, you're going to get a massive number. It equals 120,259,084,300. That is a large number, but we knew that. We knew that geometric sequences grew really quickly, and they get pretty big pretty quick. Okay, little summary. How's the explicit formula like the recursive formula? Well, again, you need the first term and you need the pattern. We have to find those things for every sequence that we do. You need to know the first term and you need to know the pattern. And now this is important here. How is the explicit formula for geometric different than explicit formula for arithmetic? I'm going to write them right next to each other just so you can compare. So the arithmetic one, it looks like f of x equals the first term plus the pattern, and then we had in parentheses x minus 1. Big font. That's not an exponent. The geometric sequence, A lot of it is similar. We start the same way with our first term. But then we are going to multiply by the pattern because it's geometric and that's what you do. Then we're going to raise it to an exponent of x minus 1. So a lot of it looks the same. I mean, if you weren't paying attention, if you were kind of zoning out, you would think they were the same. They each have the first term, they each have a pattern, they each have an x minus 1. But in the geometric, this is teeny tiny font right here. That's an exponent. It's raised up in the corner. It's smaller. It stands for multiplying over and over again. In the arithmetic one, this is not a teeny tiny font. This is big normal font that you're going to end up distributing that pattern through, and that is the multiplying is the shortcut for adding over and over and over again. So that's why that one ends up being multiplied. Okay, yep, memorize those. Keep them straight. You have to be able to write them at the drop of a hat. And like I said, it's going to be the foundation for everything we do in the next unit and 3 more this year. It's really going to be the foundation for a lot of what we do. Okay, I'm just going to give you a hint on 3 homework problems. The one that seems to cause lots of problems is number 7. Everyone's like happy-go-lucky, going along great, and then they get to number 7 and they freak out because they don't know what it means. Well, finding the xth term is just like finding the formula. It's just another way of saying, well, I don't know what that term is, but I could just write a general expression, like a formula for it. So can we write an explicit formula for this sequence? Sure. What's our first term? 4. What's our pattern? Let's see. That's multiplying by 3. Yeah, it looks like we're multiplying by 3 every time. Times by 3. So then our x term, I don't have room to write it in that box, but I'll write it right here, is our explicit formula. F of x equals the first term, which is 4. The pattern was 3, and this is geometric because I'm multiplying, so I need an exponent. Teeny tiny font. And I'm done. See? Not very hard. Okay, on the back, well, underneath those, I'm asking you to be the generator. You now have to generate a sequence. So it's kind of like the opposite. So far, I've been giving you the sequence and you've been telling me the formula, but now we're going to go the other directions. I'm giving you the formula and you have to generate the sequence. Okay, so if you think about what have we done so far every time we've had this, we had a table. Feel free to set up a table. I'm totally good with that, and I think it'll help you organize your work. I'm okay if later on, you don't have to. Here's the term number, and here's the value. Well, it says to write the first 5 terms, so I'm going to need the term 1, term 2, term 3, term 4, and term 5. And I have an explicit formula here. Well, let's look at this and analyze it a bit. I see an exponent. That tells me this is a geometric sequence. Must be multiplied over and over and over again. And I know that the thing that goes right here is my first term. That coefficient, that number in front of the parentheses, that's my first term. Guess what term 1 is? 5. Okay. What's my pattern? The pattern was the thing inside the parentheses. That's what I'm multiplying by over and over again. So 5 times 3 is 15. That's what my second term is. It's 15. So then if I multiply that by 3 again, then I would find my third term, which is 45. And so my pattern is multiplying by 3. To get from one term to the next, I'm multiplying by 3. So I could multiply 45 times 3, and then I multiply that by, so I'd get 135, and 135 times 3 is 405. But wait, just in case you don't quite put this together, there's another way you could do this. You could have used this formula. You could have said, okay, f of 1 equals 5 times 3 to the 1 minus 1 power. Put in a 1 for x. That's where you're putting in the term number of what you want. Well, 1 minus 1 is 0, and 3 to the 0 power is 1. 5 times 1 is 5. Oh, yeah, I already got that. 5. Good. Okay, well, what if I wanted to find the second term? Then I would put in a 2 here. So the second term would be 5 times 3 to the 2 minus 1 power. 2 minus 1 is 1. 3 to the first power is 3. 5 times 3 is 15. Oh, how about that? I already got it. 15. Okay? You could keep going, finding the third term, plugging in a 3 there. 3 squared is 9. 9 times 5 is 45. Exactly. So two separate ways you can do this. You can start with your first term and pull the pattern out of the equation and then find everything recursively. Or you could use this tool 5 times. And that works also. Okay, so number 9, same thing. Let's generate a sequence. You don't have to have a table. You can if you want. I think it's very helpful at this stage to just make a little table. Oh, beautiful handwriting. So neat. Very tidy. Write the first 5 terms of the sequence, and this explicit formula looks a little different than the one we did on number 8, and that's because this is arithmetic. I see a plus. I see a plus sign right there, and I don't see an exponent. That tells me this is arithmetic. And in arithmetic sequence, negative 47, that is my first term right there. That's where it lives. And my pattern is to add 8 every time. So negative 47 plus 8 is negative 39, and negative 39 plus 8 is negative 31. Let's just for kicks and giggles, let's see if we can use it as a tool, though, and find our fourth term. Our fourth term would be negative 47 plus 8 times 4 minus 1, which is 3. 8 times 3 is 24. Negative 47 plus 24 is negative 23. It works. Okay, so that's how you're going to do those. Generate your sequence. And the last one at the bottom, I'm only going to do the first one because number 20 is just like it. Don't forget what evaluate means. If I tell you A is 2, then that means that wherever A is, you replace it with the 2. And what do you know? This looks suspiciously like what we were just doing with the geometric sequence. And that's not an accident, it's on purpose. I'm trying to just have you practice a few more, making sure you know how to figure out what this answer is. So 2 minus 1, this part right here, becomes 1. 3 to the first power is 3. 4 times 3 is 12. Okay, so number 19, the answer is 12. All right, good luck with the rest of your homework, and I really hope you enjoy these sequences. I think they are a blast.